Welcome to Ask and Learn.
This problem involves a sphere, and we're going to start out by finding some average rates of change. And an average rate of change is like a standard slope, like y2 minus y1 over x2 minus x1. So for finding the rate of change from 5 to 8 for the radius measurements, what we need to do is take the volume for 8 minus the volume for 5 divided by 8 minus 5. And so we have 4/3 pi times 8 cubed minus 4/3 pi times 5 cubed divided by 3. And we'll spare you all the details from all the fraction work. You end up with 2048 pi over 3 minus 500 pi over 3 divided by 3, and that gives you 172 pi. And the units, so the volume was measured in cubic micrometers and the radius is in micrometers, so we would have cubic micrometers per micrometer. Now we're going to go with another interval. This time it's going to be from 5 to 6 micrometers. So same process, the volume at 6 minus the volume at 5 divided by 6 minus 5. So we end up with 864/3 pi minus 500/3 pi divided by 1. And that gives us 121 1/3 pi as our average rate of change. And we're going to go through this process a third time for another interval. This time it is from 5 to 5.1. So you notice that we're inching closer to 5. 5 seems to be the number of the day here. And so we're going to have the volume at 5.1 minus the volume at 5 divided by 5.1 minus 5. And we end up with, now I went ahead and approximated this one because I think that we're just kind of getting the point here. We end up with approximately 176.87 pi minus 500/3 pi over 0.1. And that's approximately 102.01 pi. So the thing to notice here is that as our interval gets smaller and smaller and we're getting closer and closer in toward r equals 5, we're getting closer to rates of change of, looks like getting closer and closer to 100 pi. So that's what part B is all about. In part B, we actually find the instantaneous rate of change at 5. So let's start by finding the derivative of the function. And remember, the function was volume equals 4/3 pi r cubed. So its derivative would be 4 pi r squared. And then when we evaluate that at 5, we have 4 times pi times 5 squared, and that is indeed 100 pi. So those other rates of change were inching their way closer to that. And that would be micrometers cubed per micrometer. Okay, for part C, we notice that the rate of change of volume was 4 pi r squared, and we know the surface area of a sphere is also 4 pi r squared. So we notice that those are equal. And we're going to take a geometric investigation into what's going on here. So you have your original sphere that had a radius of r, and then the sphere grows bigger, and now it has a radius of r plus delta r, let's say. So let's look at the change in volume. The change in volume would be the volume of the new larger sphere minus the volume of the old smaller sphere. And so the volume of the new sphere is 4/3 times pi times its radius r plus delta r cubed, and the volume of the old sphere is 4/3 pi times its radius r cubed. Now we're going to work this out algebraically. Give ourselves a little more space here. We can factor the 4/3 pi out of both terms, and we have 4/3 pi times, now we need to multiply this binomial out. We need to expand it, and we can use the binomial theorem or just multiply it out the long way, r plus delta r times r plus delta r times r plus delta r. And you're going to end up with r cubed plus 3r squared delta r plus 3r delta r squared plus delta r cubed. And we still have minus r cubed at the end from this last term here. We factored the 4/3 pi out of it. Notice that we can cancel the r cubed and the minus r cubed. And so this is delta V. This is the change in volume. What if we were interested in the change in volume over the change in x? So let's divide this by delta x. We should call it delta r, change in radius. Notice that every term has a factor of delta r in it. So if we were to cancel those delta r's, what we would have left is 4/3 pi times 3r squared plus 3r delta r plus delta r squared. That is the change in volume over the change in radius. Now, what if delta r is really small? It's very close to 0. Then this quantity is very close to 0, and this quantity is very close to 0, and what we have remaining is 4/3 pi times 3r squared, and that is 4 pi r squared.